welcome to joint TILOS HDSI colloquium. And this is also the first TILOS seminar that we have in the year 2025. So thanks for coming. So today we're really great to have Adam Kalai from OpenAI. He's currently a research scientist there working on AI safety and ethics. Now, Adam, I think he got his PhD in the surgical computer science from CMU, but then through the years, he's working on very broad range of topics, starting from algorithms, fairness, fundamental machine learning, the game theory, many other topics. He started in Georgia Tech in academia, and then he got to Chicago. Then he moved on to Microsoft and research, and then last 2 years he has been at OpenAI working on research. We made many very important contributions across those areas I mentioned, and they also received different awards, including the prestigious Sloan Fellowship. So we're really excited to hear about what's going to tell us about hallucination. So first,
thank you. Thank you so much for inviting me. It's great to be here and see a bunch of friends. This is joint work with Santosh Vempala, who's at Georgia Tech. And some of this work we did while I was still at Microsoft Research. And I've been continuing it at OpenAI. I'm going to talk about why language models hallucinate, not what to do about that. That is something I work on, but this talk is about why they hallucinate. Okay, so hallucinations. How many of you here have run into hallucinations in language models? Okay, everybody, I'm sorry. There's all kinds of examples of how that's problematically legally. People have been fined. There could be worse harms that people could have if they get bad information in various contexts. It's a problem when the expert who's supposed to defend a misinformation sources in their own testimony gets caught using AI-generated sources. So there was a court case where the lawyer who was defending and explaining the expert witness on hallucinations got caught using got caught with hallucinations. But yeah, there's so many domains where this could be a major problem. I think I don't need to motivate it for all of you since you yourselves have faced hallucinations. What are hallucinations? So there's a definition in the dictionary, and it's about some has to do with what's true and false, which these days, it's so hard to come to some kind of agreement on what's true and false, right? So for this talk, actually, we're going to go back to an old, machine learning perspective where there's just a set. There's a set of truths and or a set of errors. In machine learning, you have positives and negatives or whatever. There's a set of errors. Those are the hallucinations. And so our theory will be very general. It will apply to whatever definition of factuality you have. But it is specific in the sense that we're kind of having a model where things are either right or wrong, and there's no gray area. And the way I would explain that is we're talking about, we're giving bounds saying you'll hallucinate this often. We're saying why models hallucinate and proving lower bounds that they'll hallucinate this often. They hallucinate pretty often, even when there's no gray area. If there was a gray area, and things were even, then it would just make it worse and probably they'll hallucinate even more. So I think it's good to start with a simple model where there are things that are true, like the Declaration of Independence was signed on July 4th. There are a bunch of things which are false. The main assumption we'll make is that there's more things which are false than true. There's a lot of statements you could make which are not true. Or at least that's where we'll be able to analyze things. And you could even think of a very simple example of the distribution over statements. If you want, you could just do birthdays. Let's start with that example in mind. You have a bunch of statements. This is my birthday, April 1st. This is not my birthday. This is Misha's birthday, Sanjay's birthday. Probably not, right? No? Okay. Albert Einstein was actually born on Pi Day. So you have all these, and here's some distribution of statements. Very simple model. Even there, we'll be able to analyze the rate of hallucinations, but we'll have a theory that will hopefully give us explanations more generally. And we'll have prompts. So for now, we're just going to think of factual statements as if you prompted a chatbot and said, tell me a fact. And that's all you said, and it gave you a fact. Then after we develop the theory, I'll explain how you add prompts to it. It'll be exactly the same theory. So it will generalize to the case where you ask a question. When is Adam's birthday? When is Sanjay's birthday? And it'll generalize in that way. But let's start in the case without prompts because it's more complicated. So the errors are just an arbitrary set, okay? And then there's facts, which is everything else. Okay, so let's see if I can get rid of that thing. Oh, there it is. Is there a thing here? Did I get it? I can't see it. Oh well. Oh, top right here. Thank you. So close. I think it's not actually that thing. Oh, I have to probably switch applications. Maybe just, whatever. All right. So what are language models and what is pretraining? So there's some set of documents or texts, could actually be images, but let's just say text. And there's some true distribution. So that's the distribution that if you were training on, you would, let's think of in an ideal world even, we're going to say you hallucinate this much. So even in an ideal world where the training distribution is only factual, there's a true distribution. We don't know this distribution, we're trying to learn it, right? That's what the language model wants to learn. So we're trying to come up with some approximation of this distribution over documents. So the true distribution is P, that's the distribution over documents that we're feeding to the language model. And P hat is our approximation, the language model. It's a probability distribution. These things are very randomized. They output just random stuff. And even a chatbot, if you ask it a question, you ask it 10 times, you get 10 different answers. Yes.
Documents are like, we don't know if the documents have fake information.
No, we're going to assume that it's noiseless, meaning that I'm going to show you that hallucination is happening even when the documents are all perfectly true. So hallucinations are mysterious, okay? And there's like a gazillion reasons why they happen. So I'm going to try to bring some order to that and explain. So let's start. One of the reasons they hallucinate is because there's noise in the training data. True, there is noise in the training data, and we know that. But that's kind of obvious. Like, obviously, if you have noise in your training data, you'll hallucinate. The more interesting case is when you don't have noise in your training data, they still hallucinate, because people spend a lot of effort to remove the noise from the training data, and they still hallucinate. So I'm going to assume, for simplicity, that there is no noise. Of course, they'll hallucinate even more when there is noise, but that's the classic garbage in, garbage out thing that we're familiar with from machine learning, whereas hallucinations seem more mysterious.
What's delta?
Delta is just a set of probability distributions over some set. So I'm just saying it's probability distribution. Questions? So, and I love questions. So you can use this to complete, in general, you can give it a prompt and use this to complete a prefix. Okay, so generally there's pre-training, and in pre-training, what we're trying to do is, we're trying to maximize the likelihood of the data we've seen from the distribution over some family of neural networks or whatever, capital P. Okay, so we're maximizing the log likelihood, actually, that's important. And this thing, if you could perfectly maximize it, you would have actually learned the true distribution that the data was trained on. But you can't do that. So in practice, when we try to do this, when we try to maximize the subjective over some training set, we don't perfectly learn the distribution. Why is that, anyone? You know what I mean? And that should be a P. So like, yeah, go ahead.
Data is finite.
Yeah, you don't have enough data to learn this perfectly, right? If you had every sentence in English, if you had enough data that you've seen every document possibly, then you would learn it perfectly. But we don't. We have way too little data. So thank you. Yeah. Yeah, there's also that, right? Maybe even if we did have data, maybe we didn't perfectly converge. Perfect. Yeah. So let me just share some intuition about so weird that I can't get over there. Okay. About why language models are not actually just next word predictors. They actually predict documents. Okay. You can think of them as next word predictors, but they also predict the document in the same way that I speak one word at a time. Doesn't mean I think one word at a time. I may plan out what I'm going to say. So there's some intuition that people say, oh, they're just next word predictors. That's why they hallucinate. Not really, in my opinion, the whole story. So, you can say, look, if you want to generate a document, you have a probability model over next words, and you say the probability of the first word being the is maybe 40%. And then here's a table of, these are all true sentences. Birds have feathers and so on. We're not going to hallucinate. So I'm going to show you that it's not just because we're doing one word at a time. So you can generate from this, or you can think of this as a probability distribution over documents, because you can say the probability of the word the is 40%. The probability of the word sun, given that you started with the, is 50%. And the probability it rises then is another 50%, because there's two sentences that start with that. And so on. And you can compute the probability of a sentence. It's well defined. So if you can predict next words, you can predict documents. The distribution over documents, distribution over next words, they're mathematically equivalent. So it's not really, don't blame the fact that they're predicting one word at a time as the full story for why they're hallucinating. At least statistically, they're the same thing. Okay. And maximizing, this is just saying the same thing again, but maximizing the log probability of a document is the sum of the log probabilities of every word, or the probability of a document is the product of the probabilities of each word. So when you maximize this, maximizing next word predictor, you're basically maximizing the probability of documents. Okay, so but that is what we're doing. We're trying to find a neural network, which is a good approximation of the training data. So what does this pre-training do? It produces a predictive language model. So these language models, when you, okay, there's two, well, there's many stages, but think of training a language model as having two stages with the terrible names. One is pre-training, one is post-training, but they're both training. This one is stage 1 and one is stage 2. So stage 1, pre-training, you're trying to maximize the likelihood of your document predictions or next word predictions. It's equivalent, okay? And so you can think of that like one of these autocompletes on your phone. You know, you take your phone, it's really like a listening model. It's expecting to get data. So, you know, you type something like the declaration of, and then it gives you a few words, and basically behind the scenes, it has some probabilities for each of these words. And so that's a predictive language model. It's predicting what it's expecting you to type, okay? Or what if it's, you can use for speech recognition too, what you should hear. And then you can, you know, fill it in, and here it'll say the Declaration of Independence was signed on July, whatever. If it's a good language model, it should give you actually useful stuff. If it's a bad language model, it'll be gibberish. Similarly, you can put in, you know, Tauman Kalai was born on, and here it doesn't give you anything right. I was born in April, but it says July, and so on. So, but nobody's surprised. How would it know? It's not in the data, right? So it's intuitive. So it's a predictive language model, and it generates some things which are factually true, but other things which are not factually true. And maybe what's kind of mysterious is that, you know, usually you expect when you train something, you expect it to reflect the training data. So, but here it'll make a bunch of errors that are not in the training data. So, you know, you train it on a corpus, the corpus is in some language, let's say English, and let's say it's polite or doesn't have offensive word. And then you generate from it. It'll also be polite, grammatically correct if it does a good job, and it won't swear and so on. And it'll be accurate on some things, like the language models will not hallucinate very often on the capital of a country. You know, they know the capital of France is Paris. They're not going to get that wrong. But that's like the country, or even you can ask it, you know, when was the US founded, the dates. It doesn't screw up on all dates, like the date that some country was founded, it gets right. That's the birthday of a country. But humans' birthdays, it will hallucinate on a lot, okay? So why is it that it's mirroring some properties of the training data, but not others? Does that make sense? That's kind of the main question we're going to talk about today. So I just mentioned that there's this post-training step, the second step after you've generated this language model, which is really good at listening, where you don't want it to hallucinate. And there's all kinds of stuff you put in the second stage. This stage, you want to maximize the helpfulness and minimize the harmfulness of your language model. So, you know, if there's all kinds of knowledge in the training data about how to make bombs, but somebody asks, how do I make a bomb? You don't want to tell them how to do that, or all kinds of stuff. So there's a lot of safety, but also you want to, you know, there's a lot of inaccurate hallucination happening in the first stage. And we want in the second stage to correct that. I'm not going to talk about how we do that, but, you know, one of the things is you need to say, I don't know. And if your training data doesn't have any I don't know in it, then, or much I don't know, you're not going to get that from a pre-trained predictive model. So that's the post-training stage. So some people think that this talk or that work we've done before is trying to say, oh, hallucinations are inevitable. No, in my opinion, hallucinations are not inevitable. You could always have a language model that says, I don't know about everything. It will not hallucinate. Then you could gradually work out and say, okay, let's add the country capital. It's possible to not hallucinate.
In the perfect training data set, should we assume that entries like people's birthdays are present with the same frequency as entries like country birthdays?
Well, different peoples will be present at different rates. My birthday might be present in that data once, but Albert Einstein's birthday will be present there a ton of times. Great question, thank you.
I assume we want to keep the hallucinations for how do I name bomb? You want to keep the hallucinations?
That's a good, I haven't thought of that as a safety strategy. You're saying instead of refusing to answer somebody's question about how to make a bomb, give them false information. Yeah, go to school and study and then, well, that's a good idea. What would be good at it? I don't know. Anyway, yeah.
I used to be in the Army bomb squad and some intelligence agencies, they'll
Put
publish the
false
manuals
information.
of
Oh, that's a good idea.
purpose.
Interesting. Yeah, we haven't gotten that advanced yet. But interesting, yeah. Okay, so I'm not going to talk about what to do about that today. I'm going to talk about the origin of these hallucinations and understanding where they come from in this pre-training stage. Because I feel like that's a useful step, first of all, and it's kind of mysterious in many ways. So we're gonna, and we'll also get some rates on, like, you can think, I'll try to give you some bounds which have meaningful rates for different kinds of problems where you could understand why it's hallucinating on certain things and not on other things. Okay, so what the language model is doing is really a form of unsupervised learning, right? So it's because it's you only have positive examples. So let's say in this dream world you have no errors. Even if you did have errors, they wouldn't be marked. So let's just think of the case where you have a bunch of positive sentences or statements that are all truthful in your training data. So a language model has got this unsupervised because it doesn't have any labeled signal, it's just got positive examples. And whereas we're all familiar with supervised learning, where there's some boundary between positive and negative, and you get positives and negatives, and now you're trying to predict in the future which ones are which. Okay. So this is more like density estimation here. So now we have some distribution P over this set. It's over only facts or truthful statements, correct statements, whatever. And then we have, so I'm going to assume again that it's only over things where the function F is like the factuality function or the correctness function, whatever you want to call it. And we're going to assume that the training distribution is only over correct statements. And then we get training examples, some end training examples from this distribution. And our goal is to learn an approximation to that distribution from some family. Okay. And so we learned some density that approximates the distribution. Okay. Any questions? Now let's contrast this. Oh, sorry. And what do we want to know is the hallucination rate. So the hallucination rate is defined to be the probability that if we generate a sample from this distribution, which we approximated, it's negative. Okay. But as I said, it's kind of possible to cheat here. So can anyone give me some examples of a language model that never hallucinates besides the one I did? Yeah.
One that outputs complete gibberish.
One that outputs complete gibberish. So good. So thank you. So that would count as the gray area. So in this talk, I'm going to talk about, in the dictionary definition of hallucinations, it's like a plausible falsehood. Those are the problematic ones. Gibberish would be good, but we're going to just assume that we're only restricted to grammatical sentences, and our model is going to have like facts and factoids, which sound like they're facts, but all right, great question. Thank you. That's helpful. Okay, one that outputs a fixed single sentence from a trained set. Definitely. Okay, right. So you could just, or even a random sentence from your trained set. So you could just parrot back something from your training set and you wouldn't hallucinate. So this is not enough, so we could, as you see, we could get a language model that doesn't hallucinate. It wouldn't be a very useful language model. It wouldn't generalize at all, right? So we need to also have the utility, the fact that it generalizes, or is it actually in some sense a good model, trying to be a good model of the training distribution. So that, okay. So first of all, this is just showing you the test. So we generate from the language model and we have the tests. The yellow ones here are errors. The black ones are okay. And then there's some kind of notion of calibration and how calibrated a language model is. How many people here have heard of calibration for okay. Yeah, it's a commonly used term. I'm going to define it slightly, but I'm not going to get into great detail. And even simpler, it's like you can say how calibrated you are, but we're going to just for simplicity for the top, we're going to say, we're going to assume it's, you are calibrated. You're learning a language model, which is calibrated. And basically your probabilities have to be, calibrated is something that you can do after the fact. You can post-calibrate something. If a language model or any probability distribution isn't calibrated, you can just take all the predictions that, when the probability is in some range and you move them up or down if it's too high or too low. So it's a relatively easy thing to achieve. And okay, so this is the assumptions, basically. Noiseless data, it's coming from the training data, from this training distribution IID. And the hallucination, it's calibrated. That's the main one, that this p-hat distribution is calibrated with respect to the true distribution, which I'll define soon. And then, and this is the hallucination rate. Now let's contrast this, because we're going to actually formally connect them. We're going to contrast this to supervised learning, where you have some distribution over labeled examples. The example and the label. And so we're going to, in supervised learning, the analog is you assume the data is noiseless, that your distribution is only supported on examples where the label is correct. Okay, this is like a classic picture that you're probably familiar with. And so we get n examples from the training distribution. Now they're labeled examples. And our goal is to approximate the factuality function f here and say, if we get examples of facts and non-facts, so-and-so's birthday is this date, so-and-so's birthday is that date. Okay, and so this is classic machine learning that everyone in this institute knows about. And then you're tested on a set of examples again. But here the tests are not coming from p-hat. The tests are coming from the labeled, the x's from D. And then your goal is to figure out the probability that your label is correct, right? That's the error. And in normal supervised learning, your error is how often are you correct at predicting things. And so the errors are going to be the things in the boundary. If your function is this very simple vertical separator, then your error is going to be the points where, just crosses the line. It's just a little bit off. This is an easy example, like a easy to learn function. So you have very low error, but we'll give examples of things with high error. And the main theorem is going to be very pretty much relating these things. And I'll do that in a second, is how the hallucination rate is nearly twice the error rate of a certain classifier. So if you're 50-50, then you're not able to fact check, if you can't distinguish things that are true from things that are false based on the training data, then you're going to be hallucinating like all the time. This hallucination rate will be close to 1. If you can distinguish true from false, that's found is not very helpful. You might not be hallucinating at all. Okay, so in order to make that formal, let's do that. So the theorem is actually in some ways very simple. There's a few components that I explained. So it says for any distribution, P, which is a true distribution, as long as it's over just facts, and any calibrated distribution, p-hat, which is a language model that's approximating P, the hallucination rate, which we just defined, is going to be greater than or equal to twice the error of a certain classifier. Okay, minus this other term here. This term here, n plus is the number of facts, n minus is the number of things which are not true, falsehoods. So, for every fact about somebody and what their correct birthday is, there's 364 incorrect facts. And in fact, if you're talking about people and birthdays, there's a lot of names of people who don't even exist. And usually the number of falsehoods is way bigger. The number of things I could claim about the world is way bigger than the number of things which are true. So this fraction should be tiny. Yeah.
Is the errors the absolute number of errors or the error proportion?
Absolute number of points in the space. So think of this as a finite space, like the sentences of length, whatever. And so there's exponentially many sentences, but it's the total number of incorrect sentences, and the numerator is the total number of sentences which are factually true. We've restricted ourselves to like plausible sentences, so we don't have gibberish. Does that make sense?
But you mentioned that even if you don't have if you have a clean data set, you still hallucinate, right?
Yeah.
So for that data set, the number of errors is going to be 0, or?
Oh, no, this is just the number of, this is the number of errors in the full space. So if you were to look at, this is not in the training data. This is just the number of possible sentences you could say, which are false, which is, I ate a sandwich yesterday at Subway or something. I don't know, which is not true. Right? There's only one thing that I had every day. People tweet about all kinds of stuff, but does that make sense? Thank you. These are great questions. So this term should be super small in a lot of natural problems. If it's hallucinating paper titles, These are the actual real paper titles. These are all the hypothetical paper titles. Way more. Yeah, exactly. If you wanted to generalize it to an infinite space, you would do something like that, I think. I haven't thought about it. Good question.
Isn't n minus essentially infinite?
Yes, but the ratio is what matters. So we think about is limiting the length of the document so that there aren't infinitely many of them, then there's a finite set. And I do this bound for simplicity, but there's probably a bunch of ways to generalize this to an infinite set. And I'm glad it seems like most of you are agreeing that this term is very small. If it were infinite, then this would be 0. Okay, and then, but in order to make this formal, I need to explain what is this classifier? What is this classifier? I'm saying the error of this is bigger than the error of some classifier. What is the classifier? Well, you take the language model, whatever your language model is, and you threshold it, where at some number, which you might not be able to read, but depends on this n plus and n minus, it's some constant. And you say, look, if your language model doesn't hallucinate, then if your hallucination rate is low, then this is a good classifier. Then you threshold your classifier somewhere. You say basically when it's related to, when it's much smaller than 1 over the number of facts or number of factoids or whatever, then you're going to say it's negative. And if it's bigger than that threshold, you're going to say it's positive. So you take your language model, you say the likely statements are probably true, the unlikely statements are probably false. That's your classifier. It's a very simple classifier. Does that make sense? Okay. And so that's the classifier that we analyze and say that's accurate at distinguishing truths from falses, or vice versa. But you say your hallucination rate, if you can't classify truths from falsehoods, then your hallucination rate must be high. Now, in order to make this finally formal, there's one more thing I need to show you, which you can't read here. But what it says is that the distribution, I need to say what the distribution is here. Here we know that there's a training distribution P. Here, to talk about supervised learning, we need to have a full distribution over positives and negatives. So half the time, we're going to take a normal example from the distribution P, the training distribution, the true distribution. And half the time, we'll take a negative example, uniformly random, from the set of falsehoods, from the set of negative examples, errors. Does that make sense? Just in order to make the statement formally correct, we need to say what the distribution is. To talk about the error, we need to say, how are you evaluated? We're going to pick a random, either true or false statement. We're going to, if it's true, we pick it according to the language, the true language distribution or true positive distribution. If it's negative, we'll pick it uniformly random from the negatives, and then we'll test you on that distribution. That makes sense?
I'm slightly confused about the error function. So in the second term, the numerator is n plus square n minus, right? And you mentioned that n minus is it could be a really large number.
Yes.
So this number is actually very small.
Yeah, so this thing is tiny. So you can think of this as 0, almost ignore it. So then it's saying our hallucination rate is bigger than twice our error rate.
Oh, I'm saying the error rate. So the second term may be.
Oh, this thing is going to be, so the p hat of x, oh, so you're looking at the constants. I shouldn't put it there and just say there's some constant. But this is a geometric average of n plus and n minus, basically. It's somewhere between n plus and n minus. And so you're saying if the threshold is somewhere, like if it was a uniform distribution, it'd be 1 over n minus, basically. Is that a fire alarm? Oh, okay. I guess it's okay. Sorry, it's not okay. But I'll let everyone pause. Yeah.
Sorry, could you review the definition of f of x in the statement?
Sure. So there's some true function f, which determines what's a fact and what's not. F being plus means it's a fact. F being minus means it's a factoid or false. It's a hallucination. Okay. And so this is saying if we generate statements from your language model. So you think of this as a chatbot. And again, in this simple version, we're saying, give me a fact. And then it outputs something. And then we want to see what fraction of the time is that a real thing and what fraction of the time is it fake. F being negative means it's a falsehood. It's a hallucination. Okay. Thank you. These are all super helpful, I'm sure. Yeah.
So the constant, like you're saying, is very small, right? In FCAT?
This constant is very
No,
small.
no, the one above.
Oh, here, yeah, that should be that. It's close to 1 over the total number of the total size of the space. So it's like It's between the number of truths and the number of falsehoods. Yeah.
So like if it's approximately, it's like NQ, so it's N basically, right?
Yeah.
So then like, this 0.5 divided by a large N is very small. So what you're saying is P hat is larger than a very small number,
Right.
then it is positive.
Yeah, so the things that your language model thinks are more likely than 1/n. If there's n statements in your, yeah, n is the total, well, I haven't defined n, but n plus is the number of facts, n minus is the number of falsehoods. If it's more than, let's think of it just as like n minus. So if it's a lot more than the uniform distribution over all the falsehoods, then we're going to call it true. That makes sense?
So I guess just to follow up on that example, if let's say the n is just 2, right? You just only have true or false, right? So that number would just be what is it, 1?
No, good. So maybe that's going to help explain. So there's only true and false, but let's say these are birthday facts, and let's say there's 1 million people. So then this would be 1 million because there's 1 million true statements. Each person has 1 true birthday. Then there'd be 364 million false statements because each person, they have their true birthday, then they have their false birth, 364 days of the year they weren't born on. So this would be 364 million. So this would be, the ratio would be 1/364. It'd actually be much higher, much smaller, because then there's a gazillion people who don't exist, and we could make up statements about them too. So, but forget about that. So this would be, does that help understand? It's not the number of classes. Thank you. And it's not the number of training examples. This is the number of true statements and false statements.
So just wondering, what is the difference between F and F hat here? Can you mix the difference there?
F hat is our prediction of whether it's true or false. So we're taking the language model and we're saying, we think the statement is true if the language model says it's likely, because the language model is a probability distribution of our statements. You can actually use a language model. You used to be able to use the API and compute the probability of any statement. And you give a sentence and it'll be like, yeah, that's a really likely sentence. That's an unlikely sentence. And so this is just a simple way to say, take the sentences which are likely, we're going to call those facts. The sentences which are unlikely, we're going to call those hallucinations. And if your distribution is uniform over negative examples, then this is an okay way to distinguish facts from hallucinations. Well, it's a way to distinguish facts from hallucinations.
So is the idea to chain this with some kind of lower bound on the supervised problem?
We will get there. Yes, great question.
So I'm still wanting to confirm the n plus n. So the x, is it conditional on one person? For example, if I'm asking.
Right.
your-
So this version is the version where there's no question. It's just tell me a fact. It's always the same prompt, and it outputs a fact. Oh, so and so was born on that date, or tell me some birthday fact. Then we will get to the version where you can ask about a certain person. The version, and I may not have time, but the version where you query about a specific person, this is the number of true answers for that person and the number of false answers for that person. So in that version, it would be like 1/364. Thank you, that's helpful. Yeah. Yeah. Neil.
How important is the importance?
That's a good question. There's so many directions we can loosen our bounds, and we do have ways to do that. And so you can have some kind of R regularity condition that we have, and we get bounds that like generalize it in that way. So I'm kind of trying to present the simplest analysis. Also, the distribution may not be perfectly calibrated, but the more important one that we do discuss in detail is the fact that there are many prompts. So you might actually ask a specific question. Well, let me keep going, and then, but I'll continue to take questions in a second. But let's look at this again without the F hat. Look at this distribution problem. What a tough problem we're in. When we only see the positives and we have no idea where the negatives are. Look at this. Suppose the negatives were here, then it's fine, everything's good. But what if the negatives were over there? That's a really hard supervised learning problem. We don't know how to separate. And we can't even distinguish these two problems when we're in the unsupervised setting, because when the language model is learning, it's only learning from positive examples. Learning from positive examples is harder than learning from positive and negative examples, right? You just have less information. So this is a tough problem. So you have to have some sympathy for the language model. So it's kind of interesting. So in order to understand how much a language model will hallucinate, you have to do this thought experiment and say to yourself, would I be able to distinguish positive from negative examples? Would I be able to distinguish from the training data if would I be able to distinguish, real birthdays from false birthdays or real, whatever the questions are? So, okay, I have a slide on what calibration is, but I also have a lot more material to cover. So in the interest of time, I'm just going to kind of zoom through it. So basically, the intuition behind calibration is you say, oh, well, originally it's like a weather forecaster predicting rain with 20% probability. And then if they say that, then on 20% of those days, it should rain. So it's actually easy to be calibrated because you can, if you know the average probability in the year of rain, you can just predict that every day, and you'll be calibrated because on days where you predict if it was 20%, then on days where you predict 20%, on average it's 20%. Now, if you get that number wrong, you won't be calibrated, but you can always post-calibrate something, a weather forecaster, by just monotonically transforming their prediction. So there's algorithms that do that, and neural nets do that automatically. And so our definition of calibration is like that for facts, where you say, on average, when you predict, the language model predicts some statement or some text Z, or some text with probability Z, on average, overall statements with probability Z, it occurs with that probability on average, and there's bucketing and all kinds of stuff. There's also experiments, GPT-4, the tech report. People do experiments. It's not exactly the same notion of calibration, but they show that the pre-trained language models are in fact calibrated. And there's some mathematical reason why, which is that if you post-calibrate something, the training loss goes down. So calibration is just like a way to think about doing an okay job at pre-training. It's not even great. You can, again, as I said, you could pick the uniform distribution over a set will be calibrated, but it's like a minimal condition. It's like sanity check. It's saying, are you calibrated? Yeah, everything looks good. The after post-training, the actual language model we use in practice is not calibrated, and it has to be not calibrated based on our theorem, because otherwise you're going to hallucinate a lot. So you don't want your chatbot that you actually release to be calibrated. And that's the case for post-training procedures. Okay, so we have this theorem. Again, this is some tiny term, and we say our hallucination rate is at least twice our error minus epsilon. So let's think about the interpretation. The interpretation is that if this is an unlearnable problem, if it's just statistically impossible to learn, then you'll hallucinate, which is kind of interesting because hallucinations on the one hand seem kind of mysterious. On the other hand, the fact that there are some distributions that you can't learn, that's a very familiar idea to us. There are some problems where we don't expect to get 100% accuracy. There are some problems where we do. And so, and there's a lot of stuff in between. So that's just kind of borrowing the intuition we have from supervised learning and porting it over to this language model setting. It's a little stronger because it's not just what's unlearnable. There are some problems which are learnable, but you fail to learn it. Okay, so you maybe your classifier didn't converge, like you mentioned, for computational reasons, or you did gradient descent and it landed in a bad local minimum. Well, if that thing failed to learn, so if you threshold your language model and it's doing a bad job at distinguishing positives from negatives, then it's also hallucinating. So it's a computational statement as well. It's saying that getting the language model to not hallucinate, avoiding hallucinations is as hard as avoiding misclassifications and avoiding errors. So that makes sense. Okay. So, maybe what you have here is, you learned a bad, even though this is an easy problem, maybe you learned a bad bad language model, which is put stuff all over here. So then it's going to hallucinate a lot because it did a bad job at separating these positives and negatives. Let's look at some more. We can generally port the intuition. So what are the types of failures we have in learning? You have the noisy training data you mentioned, garbage in, garbage out. Well, you have your test data may be out of distribution. And these will all, you can think of an analog in hallucinations. These are kind of the easy, obvious ones. I mean, there's still problems, but your model class might be bad. So if you're learning vertical separate, if your language model is a very vertical language model here, we have to assign probabilities based on the vertical space, but the truth is horizontal, you're in trouble. That's another type of failure. And if your language model is similar, we'll get to examples of that. You could have a poor model fit, as I mentioned. And then the most interesting one, in my opinion, is the statistical complexity example where there's some high VC dimension. So the every class of functions has some inherent number of parameters, and some are much larger. And the classic thing of statistics is you need an amount of data related to how many parameters are in the true thing. If the birthday table, if there's 1 million people, you need to see 1 million examples to learn all their birthdays, because you got to have so that's the statistical complexity. And then there's a bunch of types of hallucinations. So like there's statement, humans use 10% of their brain. If that's in your training data, then that would be like the garbage in, garbage out analog. You have noisy training data. So what are you going to do? Here's a statement that a language model would probably hallucinate on. What's the cube root of, this thing? That's because, and that's sometimes called an intrinsic hallucination. It's not based on some fact, some statistical fact knowledge. It's based on a miscalculation, basically. And that's because your class of transformers, if you use transformers for language models, is not capable of doing that, right? If you use transformers that were augmented with calculators, maybe it could do that. But if you don't, then there are 2 R's in strawberry. Does anyone have an opinion on what? I mean, these aren't absolute rules. And now I'm just showing you that you can port the intuition. So maybe people have different opinions on what the source of this is. But why would a language model think there's only 2 R's in strawberry? There's actually 3 R's. Say it again. Why model fit? Oh, because it just missed. Because they can't count. Everything. Oh, okay. Anyone else? Tokenization. That's another issue. Yeah, so I think you're both right. So one is that it didn't do a great job. If you train this, even also OOD, if you train this on a gazillion examples like this, it might learn it. But the issue is that the language model breaks this word strawberry not into letters, but actually into chunks. And think about it, it has to just like backwards figure out how many, the chunk is just a number to it. So it doesn't know what letters are in that chunk. So its only ability to figure out how many R's is through some very complicated reasoning and solving of some puzzle. So anyway, I think of that as model, another intrinsic model. Okay, and hallucinated references. Actually, I think that's a poor model class or poor model fit. I think that problem is solvable, and I'll explain why. Misha, who's here, whose birthday it says is August 4th, that one is the most interesting example. That's a statistical VC dimension. The birthday class has very high VC dimension. And so those are the kind of ones that I think are the most surprising, maybe. All right, so the main theorem, I'll just mention that we can extend it to the case of question and answer prompts. So in the main theorem, you say there's some question. So that's like dividing up the space into horizontal bands. And each band depends on the prompt that you say. And then you say, look, okay, each band we need, we have the same, and then for each question, we have an answer. And now we're just going to assume the questions are drawn from the true distribution P. And the answers we get the language model is generating. So our notion of correctness of hallucination is now going to be, it's not super important you understand this, but it's a way of generalizing the previous thing. It's saying, look, what's the chance of a hallucination? We're going to draw a question from the true distribution P, and then we're going to draw an answer according to our language model. And we're looking at the probability that if you take a question from the true distribution answer from our language model, you get a falsehood, an error. And all the same analysis works exactly the same way. So just with the same bounds. Okay, so if you ask a language model, what is Professor Misha Belkin's birthday? And you tell it to answer with just month, day. Okay, that's what this says. Then I wonder if I turn up my volume, maybe that thing will disappear. But now am I getting feedback? That's okay. No, oh, kind of. Anyway, so all right. So so basically, I went to this language model arena website, which and I asked it like, what is Professor Misha Belkin's birthday? Is your birthday online? No. Okay. So Gemini language model, and I say just answer with month, day. Gemini model said 0504, May 4th. Is that right? No. Mistral said June 19th. No. Quen model said September 28th. No. Goblin, January 17th. No. Okay. These are all pre-trained language models. Claude said a long answer. I should note that since this is a very specific personal detail about an academic figure, I could be hallucinating this information. I'd recommend verifying it independently August 15th. I was very happy ChatGPT on this one. ChatGPT does hallucinate a lot, but on this one it said, sorry, I can't provide that information.
Maybe
Yeah, you could probably make it. And then, you know, I went back and I asked them again and I regenerated. And the funny thing was you get totally different answers from each of these models. So this is getting into the direction of how could you address this? I mean, clearly the language model knows or should know that it doesn't know the answer if you ask it 3 times and it gives you 3 different answers. Are any of these right, Misha? When is your birthday? If you don't mind saying. November 5th. Okay, well, we'll have to have a birthday party for you now. Okay, so yeah, so this is just to show you that this is a real problem, and even this birthday example, so simple, is happening here, but all the other types of hallucination happen as well. Okay, so now I'll give you that estimate of the learning rate. How much time do I have left? Do you know? 10 minutes. Okay. So now we'll get into the rate. Now, okay, that was an interesting connection between these 2 spaces, but still, how often are we hallucinating? Well, who knows how often we'll be right or wrong. So one kind of problem, which is really hard to learn, is like the birthday kind of problem, where the reality is pretty independent. You know, Misha's birthday being November 5th is pretty independent of everyone else's birthday here. It's just like a massive lookup table. They're just facts and they're unrelated. And in that case, it's very hard to do supervised learning sometimes. Well, it depends actually. So when the countries were founded, their birthdays, they're independent maybe too. I don't know if they're independent, but actually it's not that hard to learn because they're repeated so many times in the training data, right? So Alan Turing came up with a very clever estimate of what probability, well, he came up with a clever estimate that we can use for bounding the hallucination rate when you have facts that the assumption is that there's like a right answer. We could generalize this, but for simplicity, let's say there's one right answer for each question, and there's n minus some number, n minus, let's say 364 wrong answers for each question. Okay, and then and we're going to assume that the correct answers are random in that set. Again, we could generalize this like Neil was probably imagining, you know, it could be non-uniform. Like there's lots of ways to generalize it. But let's just say for simplicity, there's a set of the incorrect answers and one correct answer. So the number of answers is n minus plus 1. And the true one is one of those at random. That's your chance of getting it right. 1 out of n minus 1 plus 1. And okay, and then and they're assuming independence. But the fraction of times that any question is asked is not, we're not making any assumptions on that. Alan Turing, people will ask about his birthday a lot more than they'll ask about my birthday. Apparently, people have been asking about Misha Belkin's birthday. No, but this is the fraction of times it appears in the training data. And we're also assuming, it's not written here, sorry, that's the fraction of times people are asking about that same thing. So we're assuming a match between the training, your training distribution here is ideal. So this is, I'm not sure if people are familiar, there's something called distilling that people sometimes do. Like, what is the perfect training distribution for a language model? Maybe it's literally a bunch of chats between users and having factually correct ideal responses. That's this model. People do that. That's a way that some language models have been trained. They do perform well in that regime. And so even in that regime, this is a good estimate of the fraction of the rate of hallucinations. So your hallucination rate is the fraction of examples that appear exactly once in the training data. Does that make sense? So Alan Turing will appear like a gazillion times. Einstein will appear a gazillion times in the training data, his birthday. My birthday might not appear, or if it does, it's going to be just once. There'll be a bunch of nobodies like me whose birthday maybe appears once or maybe not at all. And you're really in trouble on the people whose birthday doesn't appear at all because you have no chance of guessing them. Your error rate. So what's your error rate in this thing is, it's really easy to analyze it because you say, look, I've got some things which appeared, but anything which didn't appear, I'm in trouble. There's no way I'm going to be able to guess that accurately. And so if you plug in this analysis, if this is a corollary of that theorem, then you get the bound like this. Does that make sense? Okay. And so I'm gonna skip this because I think I'm almost out of time, right? I got like 1 minute.
Have 6 minutes.
Oh, 5, 6 minutes. Okay, so let's do so there was a bound from Alan Turing, and it's generally called the missing mass estimator, and I recommend you look into it. But that we just apply, basically we're combining known techniques. We're applying Alan Turing's estimate with a bound from David McAllister and Rob Shapiri, and plugging it into our theorem to get that statement. But there's the neat part is the interpretation. So what we're saying is that the hallucination rate after you've pre-trained is almost this rare fact rate. How many fraction of facts appear just once, and minus some small number. And okay, so now we can think about what type of statements would just appear often just once in the training data. So country capitals or country founding dates, would they appear just once or many times? Many times. So the rare facts would be like 0 or very small. So we wouldn't expect hallucinations there, and that's what we get. What about for book and article titles? So I said, give me a paper about something, a book about something. Do you expect most books and articles to appear once in the training data, or many times, or never? What do you think?
More than once, mostly due to cross-referencing.
Yeah, but I mean, every paper I write, even if it's never cited, I put it on my webpage, I put it on Archive, it's on my CV, I'll put it on, a bunch of these websites. So yeah, I mean, the point of publishing something is you're trying to advertise it, especially books, right? Like who writes a book and doesn't have it try to, advertise it all over the place. So my intuition and my belief is that books and articles appear many times, and yet so the rare fact rate should be very small. So this bound says that the hallucination rate is at least that. So my belief is that the language models don't need to hallucinate on those. They're just doing it. It's a bad model. Like a better model than a neural net for that thing would be a lookup table, like a database that stores all of those things. And then when you ask, it goes and checks it. But we use these transformers, and they not only have to remember all the titles of all books and everything, they have to memorize a bunch of other stuff, so they just don't have the capacity, I think, to memorize everything like that. So it's kind of so that's an opportunity, basically. Hey, we should be able to improve. We know that we should be able to improve even from pre-training on those. Birthdays, it's a heavy tail distribution. Basically, there's a lot of people. There's some whatever fraction of celebrities. If a third of the mentions of birthdays on the web are celebrities, then you would expect to hallucinate 2/3 of the time from the pre-trained model. Again, the post-training just adds something which somehow checks and should not hallucinate. Like it could generate 3 answers, look at them and see if they're all the same. If not, no. Okay, so what about adding new facts to the training data? Would that reduce or increase hallucination? So what if we said, oh, let's go get a bunch of birthdays from the Social Security office and add that to the training data to make our model more accurate? Will that increase hallucinations or? Yeah, it'll increase counterintuitively. Oh, I got all this great data. I'm going and throwing it into the training data, but actually now the model, as a good statistician, says, oh, I'm trying to predict what's coming out, what somebody's going to type next. So I expect them just to pick another random name I've never seen the other day. So it's kind of funny. It actually hurts. Duplicating training data, going over the training data many times will help, because now things appear, or if you think of it sampling from a distribution over and over and many times, then you've got a distribution, you're going to just overfit and memorize the training data. You won't generalize, but you'll have fewer hallucinations. So in summary, there's this pre-training, which causes errors or naturally leads to errors. And then there's post-training, which we didn't talk about, but that should avoid them. And connecting supervised learning to unsupervised learning helps us hopefully understand and make it a little less counterintuitive, or bring in the intuitions that we have from machine learning and statistics, where it's not surprising that our classifiers sometimes have errors, and we know there's a gazillion reasons why they could have errors, but we know what they are and they all make sense to us because there's been some, you've all taken a number of classes in machine learning, and there's all these reasons: bad data, garbage in, garbage out, you have a bad model, you have VC dimension, and all those reasons transfer over to why language models hallucinate. So if you are misclassifying, you're going to generate errors. Conversely, it got some intuition why they don't screw up on grammar or some rule like that. It's kind of amazing, but they did learn good grammar. They did learn politeness. These are things which presumably are learnable in a classification sense. If you can't reliably fact check, then our theorem says you'll get errors, and we have this bound, which connects the hallucination rate to the fraction of facts that appear once. And I'll just conclude by saying that there's an analogy to the human brain. The human brain, this is a little bit of character, maybe Sandra can, or somebody here can correct me, is that, there's two parts. The old view is that there are two language models in the brain. One closer to the ear for listening, called the Wernicke's area, and one closer to the front, called Broca's area, which is the mouth. But if you just take facts from listening, this language model should be good at predicting what it's supposed to hear. And actually, there's a condition that people sometimes have called Wernicke's aphasia, where they are basically generating from this part, and they also hallucinate. But in general, people don't do that because we have this separate language model for production. You have one model so you can hear what people are saying, and you expect to hear a bunch of facts that you didn't know. The production part, you have to say things only that you know. And the big question of alignment or post-training is, how do you take this predictive language model and transform it into something useful? It's already amazing that it's kind of useful with very little transformation, but the question is, what do we want these things to say, given that we don't want them to match the training distribution? And so that's a big open question in this field that I leave to you guys. What I want to say is thank you very much.
Thank you for the talk. Yeah, so questions?
You kind of touched on this earlier. Is it reasonable to say that the class of hallucination X's are those whose truth probability is independent of all the other X's?
So you are in trouble if there's no way to determine, your X from that. Now, there could be cases where it's possible to learn, let's say you're doing math, you're trying to learn how to do multiplication, and the language model can't learn that because it's just too hard for it. It's determined, the probability is determined, and a smarter model would figure that out, but because you're learning a model which isn't smart enough, it fails. So that's another kind of reason. Did that make sense? But then that first intuition is most of the cases of hallucination, I would say. Yeah, going back. Yeah. So. Yeah, I mean, you could say to yourself, is this something, first, is this category of questions something that I could determine normally from the training data? I mean, how does a human know? If you ask me when Misha's birthday is, I know I don't know it, right? And I know that because I know that it's not something I can determine from my other knowledge. So it's sort of, maybe, it's a very good question. I think you could, I don't want to get into all the strategies we have for addressing hallucinations, but I do feel that in our work on trying to address hallucinations, it's helpful to understand. But yeah. Oh, wait, sorry. Let me go back there because there's a question back there that person has asked a question.
I mean, this version of video generated models, they are the same politeness and post-training large language models, and you think the same kind of model or regressive.
Maybe. I mean, the question was about hallucinations in video generation or image generation, like where you have like way too many fingers or weird unnatural things. Yeah, I think so. And I think that would, if you were say, I can't, if a model can't distinguish those from realistic, that people have 10 fingers, not 12, that would be probably a case of model fit, like the model, maybe you could train a model to distinguish those, but for some reason, it didn't hone in on that as a primary thing to look at. Humans are very sensitive to that. There's probably a lot of issues with the videos they generate, but we notice fingers very prominently, and so the language model just didn't pick up on that for some reason. But yeah, I think it's the same phenomenon. Yeah. Okay.
So in practice, is there any way to go about sort of benchmarking hallucination?
There's a lot of benchmarks for hallucination. Yeah, there's a ton. I mean, the simplest is you just take a bunch of facts from real world and then judge the language model. Oftentimes, the evaluation will use a language model, because you say write a bio about Misha Belkin and it'll give you like a gazillion facts, and then the thing will pull them out and check against Wikipedia or whatever. And there's like a lot of them. Yeah.
Is this why like models that sort of refine their predictions or make multiple predictions prior to outputting an answer seem to be so effective at correcting their hallucinations?
Great question. So the language models do seem to be better at realizing after they said something. Like you saw, you generate 3 birthdays, they're all different. You can even literally ask a language model after it generates something like, do you think what you just said is true? And sometimes it'd be like, actually, okay. So if you have, I don't know if we're going, but if you have a chain of thought where it sort of thinks things through and then says, well, I know I said that, but I'm not sure that it's right. It's very non-human. Like we don't do that as much. We usually do this sort of contemplation. Do I actually know whether somebody's birthday is on a certain date? But yeah, that I think that is a big factor in why they go down. But I don't know how that, it's an interesting question. I haven't thought about how that relates to this theory.
If you like assume that like the bound, let's say weirdly you assume that each prediction was independent, right?
Yeah.
Then the multiplicative, you're now multiplying probabilities and the ultimate final probability of hallucination.
Yeah. Some of the mitigations that people have published is generate 10 answers and check for consistency for 3 answers. And that would definitely address that. Yeah.
So take one last question and then we'll
Okay.
then take the other questions offline. So because the
Yeah, whoever wants.
maybe I'll give the one over there. Do you have a question? Okay, then maybe.
Somebody who hasn't asked a question, yeah.
As an AI safety researcher, do you think, so I guess a general question, these issues with safety, why is more particular? The person to this topic is hallucination. Do you think it's solvable by just creating quote-unquote better models as we get closer to AGI? Or is this something that we should address as we evolve?
I think we definitely should address hallucinations. I also think if you look at all the evaluations of hallucinations, they're getting better. The models are hallucinating less than before. They're still hallucinating a lot. It's terrible. I struggle with it every day. But well, your question is whether them getting better will naturally reduce hallucination. I think it, or is that your question?
Said it's models are getting better, hallucinating less.
Yeah.
I can pose this question as, is that an artifact of researchers working on hallucination in particular? Or is it because
well, people are working on a lot of benchmarks in language modeling or correctness on tests or something like that. No, they're not. So I don't think it's a result of bigger models. I don't think just making a bigger model. This theory says that like bigger models, they might help with some types of hallucination, but they generally won't solve the problem. But the using chains of thought or something like that. I mean, I think that the what I see is that the recognition of hallucinations as a problem in industry is going up. Now that we fixing like a lot of other problems, used to get a lot of nonsense or stuff out of the language model that was wrong in many ways. And now it's getting correct, it's able to do all kinds of, most of the things right. And then this hallucination problem is a glaring, like a very serious problem. So I think there's more attention on it now. I think there wasn't enough attention on it before in industry, but that was even before I joined OpenAI. Thank you very much.
Thank the speaker again.